Okay. All right, guys. Thanks for coming. We got a good crowd here today for the review. Just want to say a few things about the exam. And mostly what we're going to do in the next couple hours is just practice some problems. I just want to do some examples. Obviously, as you've been reviewing the review packet, there are the theorems that you're supposed to learn for the test. And because those are in your notes and it's kind of up to you to just on your own learn those and practice those and kind of get those down, I'm not going to really talk about that so much today because that's kind of what I want you guys to focus on. Of course, if you have any questions about those proofs, you can definitely ask me. If you're wondering, do I need to prove this, or can I just, what's obvious, what's not obvious? Feel free to ask me about that. But I want everybody to work really hard to get those problems, those two proofs totally correct. Because that's going to be like a good chunk of your points for the exam. Okay? So anyway, so there's the theorems that you're learning, and then hopefully you've been going through the review packet itself. Kind of check. I would go through the bullet points on the review packet and just check them off as you start to get more comfortable with those things, as you feel better about them. Go back to your notes and review things about, the Euclidean algorithm, canceling from a congruence equation, Wilson's theorem, yada yada yada, all that kind of stuff. So there's a whole bunch of a whole bunch of things there about what you should be able to do. And then there's the sample problems as well as the sample midterm. So you have lots of other problems to practice, but believe it or not, I've come with a whole bunch more problems that you haven't seen yet. So that's kind of the idea of this, is to focus more on the roughly 75% of the exam that's going to be new problems and give you some practice with that. Obviously, I'm not going to be asking you exactly these same questions, but they're going to be using these same kinds of ideas, right? So that's what I want to focus on. Also, the idea of the review session is not that you're going to walk out of here ready to go throw a party tomorrow or anything, right? The idea is going to be you're going to go home and know what you need to focus on, right? Where you need to spend a little time between now and Monday to get ready for the test. I may not talk about absolutely everything that is absolutely from the beginning of the semester until now. I'm going to talk about a lot of stuff, but I just want to point out, it doesn't mean just because I didn't talk about something doesn't mean I won't ask you about it. Okay, I'm just going to give you the flavor of everything that I have time to do with these problems, but I'm not promising that this is absolutely, totally, thoroughly complete. Okay, so anybody have any questions so far? The sample test will give you a good idea about the length of the thing. Again, if you can try to show up a little bit early, I can get you started a little bit early on Monday, and I'll try to give you a few extra minutes at the end as well. So that way we can stretch the time as long as possible. So, okay. Why don't I just start into my practice problems here? By the way, this is a very informal thing. I'm in no hurry. If you have questions, this is a great time to ask them. Don't feel like you're slowing me down or holding me back. I'm in no particular rush. So we'll just take our time and kind of casual and relaxed approach to this. Okay. So let's just take a few examples here. Okay. So let me just start. I'll start over here with the first one. I made up some problems ahead of time, and I'm not necessarily going to go directly in order, but I will try to somewhat go in order here. So here's the first one. There's two parts to this one. Is there a solution to the congruence x squared congruent to 2 modulo 16,072? You remember on Wednesday we were talking about whether or not the number -1 has a square root mod p. And it turns out that last theorem in theorem 5.5 tells us, well, yeah, it does if p is congruent to 1 mod 4. Right? So there's that kind of theorem. Well, this is just asking, does the number 2 have a square root in the mod of 16,072? Okay? So if you saw a problem like that, what might you do first, or think of doing first? Okay, why are you doing that? No. The theorem says that x squared plus 1 congruent to 0 will have a solution mod p. P is a prime, by the way. If and only if p is congruent to 1 mod 4. So does this theorem have anything to do with that problem? Probably not, because the mod over here, this is not prime, right? We can tell that. Okay, so does anybody have a suggestion of what we should try to do first? Cheyenne?
Had 2 been a square, I would have been happier with this problem, because if it was like a 4, you could split it up with the difference of squares once you subtract 2 to both sides.
Well, if this was a 4, then we'd have a solution which would just be 2. Yeah, this is a little harder than that. What's the very first thing we should do? Yeah, you need to take this modulus and decompose it. You need to factorize that number. Absolutely the first thing you should do on any problem like this. Especially if you don't know how this number factorizes, that's a very important thing to do. And you're not going to have a calculator, so we're going to have to like brute force this thing. Okay? So, take your time with this and see 16,072. It's clearly divisible by 2. And in fact, remember that, so a number is divisible by 2 if it ends in an even number. It's divisible by 4 if the last 2 digits form a number that's divisible by 4. It's divisible by 8 if the last 3 digits form a number that is divisible by 8, and so on and so forth. This number, 72, is divisible by 8, right? It does divide at 8. So this thing is at least divisible by 8. So I'm just going to do long division here, and I'm going to get 2009 out of that. Okay, so I have 8 times 2009. I may or may not be done with my factorization. I have to look at 2009 and see whether or not that number factorizes in, or has any prime factors as well. So we can look at that. Does this thing factor? Well, I don't know. It's obviously not divisible by 2 or 3 or 5. Maybe it's divisible by 7. Let's try it. Oh, it is. 7 goes in there 287 times, all right? And then 287 is actually also divisible by 7, goes in there 41 times. So the first thing is we factor this number. It is 2 cubed, that would be 8. You want to factor it completely into primes, right? So 2 to the 3rd power times 7 to the squared power, and then 41 is also a prime. Okay, so we factorize it like that. So far so good? Okay. So, any suggestions what we might do next? Okay, we could certainly look at this congruence. Mod 2 cubed would be 8, and we could look at it mod 49. And then we can look at it mod 41, right? All 3 of these mods. If we could find a solution that satisfies each of these, then by the Chinese remainder theorem, that same value of x squared would satisfy the same congruence modulo the product of these mods. See, these mods now, guys, are pairwise relatively prime. Right? Because 8 and 49 have nothing in common, 8 and 41 have nothing in common, and 49 and 41 have nothing in common. That's because you've split off the different prime powers. Okay? Everybody with me so far? So you have to break down the 16,072 into its prime factorization. Now, of course, mod 41 is a prime, so I do know that anything to the 40th power would be congruent to 1 modulo 41, but unfortunately we're only looking at the 2nd power here. So that's not quite so helpful. So Fermat's little theorem isn't really helping me very, very easily here. Here we don't have a prime. These are not primes, these are powers of primes. So Fermat's little theorem is not looking so useful at the moment. So does anybody have a thought as to what we could maybe try to do here? You know, your best friend is whenever you have a small mod. A small mod is really good because when you have a small mod, in the world of mod 8, there's only 8 different numbers, right? Which are 0, 1, 2, 3, 4, 5, 6, and 7. If you actually take just this first congruence alone, we could try to see, is that even solvable? This doesn't say find a solution. It just says, is there a solution? Is there a solution? So, is there even a solution to this? What's 0 squared?
0.
Is that a solution? No. What's 1 squared? 1, that's not congruent to 2. 2 squared, doesn't work. 3 squared, doesn't work. 4 squared is 16, that's not the same as 2 mod 8. 5 squared, doesn't work. 6 squared, which is 36. 36 is not congruent to 2 mod 8. 7 squared, nope, doesn't work. Nothing works, right? So this thing doesn't even have a solution mod 8, let alone, so in other words, what we're saying is by brute force, now you will not have a calculator to use, so be careful about brute force, because if the mod is big, it's going to take a long time. That's why I chose mod 8. Why didn't I check everything up to 40, 41? Well, it's because it would take too long, right? Let's just check mod 8. By brute force, x squared congruent to 2 mod 8 has no solution. In other words, what does that really mean? It just means that 8 does not divide x squared minus 2. And this would be for all x. So for every integer x, 8 will fail to divide it. If 8 doesn't divide it, if 8 does not divide this number, then surely 16,072 isn't going to divide that number. Guys, if 16,072, if that divided x squared minus 2, if this was true, well then, by the transitive property of divisibility, 8 would have had to divide it also. The fact that 8 does not divide x squared minus 2 means that this larger number also cannot divide x squared minus 2. So I'm just going to say here, thus, 16,072 does not divide x squared minus 2. The answer to this question is no. It is no. There is no solution to that congruence. The number 2 does not have a square root in the world of mod 8. Okay? Is everybody with me? Okay, great. Now that we're warmed up, let's try a part B. Try another example. And just interrupt me with questions. Part of the idea of bringing you these problems is, it's not so much just about solving the problems, but it's also about perhaps inspiring some of your questions as we go along. So don't hesitate to ask. So here we go. Is there a solution, do another part to this. Is there a solution to x to the 4th plus 5x cubed plus 4x squared minus 4x minus 3 congruent to 0 mod 52? Another yes-no question here. All right, try this one. Okay, now that we've done part A, let's see if we can do this one a little bit faster. Does anybody have a suggestion what I might want to do first? Say again? Got to factor 52, right? I'm going to factor 52. Exactly. So let's try that. 52, this one's pretty easy to factor. You take out a factor of 2 twice, right? So it's 2 squared times 13. Okay? Which of those, which mod do you think is our friendliest mod to work with here? 4. You always want smaller mods, right? So in other words, if there's a solution mod 52, then there would have to be a solution mod 4. Let's just look at this thing mod 4. So in mod 4, right, in that mod, x to the 4th plus 5x cubed plus 4x squared minus 4x minus 3, we can reduce it, right? I can rewrite it as x to the 4th plus x cubed, and then, well, 0 and 0, and then minus 3 is the same as plus 1 in mod 4. In mod 4, right? Normally, guys, if you were trying to solve this, you would be, trying to factor it. If you were an algebra student in high school, you'd be trying to factor this system or whatever, play some tricks with the algebra. But see, if we're working in mod 4, there's only 3 numbers, well, there's 4 numbers that we have to try. Plug in 0, does it, so the question is this congruent to 0 in the world of mod 4? Well, we just tried the numbers 0, 1, 2, and 3, and we're going to find out, okay? So does 0 work here? If I put 0 for x? No. If I put 1 for x, does it work?
No.
No, because 1 plus 1 plus 1 would be 0. Now we have to work a little harder here. 2, okay, I got to take 2 to the 4th plus 2 cubed plus 1. This is going to be 16 plus 8 plus 1, that's 25. Actually, you know that 2 won't work because you're going to get an odd number here, and an odd number won't be congruent to 0 mod 4, so 2 doesn't work. What about 3? Well, actually, I wouldn't even do 3. Change 3 to -1 and do that instead. Okay? I'm saving you time on the exam, right? I don't want to take 3 to the 4th. Let's take -1 to the 4th. -1 to the 4th would be 1. -1 cubed would be -1. And then I'm adding 1 again. That does not add up to 0, right? So there are no solutions. By brute force, there are no solutions here. If there's no solutions mod 4, then there's definitely no solutions mod 52. We don't have to check this one. No need to check this. Okay? So no need to check the 13. We just check mod 4 only. That's all we have to check. We just plug in 0, 1, 2, and 3, and we got no, 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 and no. Right? None of those work. When you plug these numbers in for x, none of them work. Does it make sense? Okay. So those are the first 2 examples. Those are both no. Yeah, Casey.
If it was,
If we did get a solution?
would we just have to check 13 by brute force?
Right, if 4 worked, and we did find an x that worked mod 4, well then we would have to check mod 13, right? And mod 13 for an equation like this, it would take a little bit of effort, wouldn't it? Yeah. So chances are it wouldn't make a very good question to do without a calculator in that case. Okay. We're going to be doing a lot of problems today involving congruences and modular arithmetic, so this is just getting us warmed up. I have some really, really good questions here. Okay. I like these problems. I wanted to save them for the test, but then I'm like, no, I have to show you these questions. Okay. Let's try this one. Okay, so here is true or this is also part A and part B. True or false? There exists an x in the positive integers such that, true or false, there exists an x in the positive integers such that x plus 6, and x plus 12, those 3 numbers, so these 3 numbers, is it true that there exists an x such that these are all prime? This is the question. Can we find a number for x so that all 3 of those numbers are prime numbers? I'll let you guys think about it for a second. I don't want to spoil the fun too quickly. How many people think they know the answer already? Just me. Okay, I'll give you a little more time. Think about it. I want all of those numbers to be prime. Anybody think they have it yet? Do you have the answer? Is it true or false?
It's true.
It's true, okay. So what would x be?
7.
7?
Yeah.
Oh, okay, x is 7, you add 6 to that, then you get
13.
13, and you add 6 to that, you get 19. Those are all prime. Okay, it's true. Pretty straightforward, right? Okay, actually I think 5 would have worked also. X equals 5, x equals 7. There's lots of right answers. So that one is pretty easy, but it's really meant as the warm-up for the next part. So here's part B now. This is where the fun begins. Okay? True or false again. Okay? Oh, so when something's true like this and they're supposed to show that there exists something, all you have to do is show, you don't have to give me a derivation. You don't have to derive, how did you come up with x equals 7? Right? It's perfectly acceptable to say, well, I came up with it by just playing around with numbers. Okay? Okay, you don't have, there's really nothing, you're not using any big theorem here, right? You're just literally just trying a number and it worked. Okay, let's try this one though. There exists an x in z plus such that x plus 6, x plus 12, x plus 18, x plus 24, and x plus 30 are all prime. Okay. So I will erase some space here while you guys think about that one. Now we're adding more numbers here. Now we want all 6 of these numbers to be primes. Okay? I guess the first thing I would do is check 7. Because the first 3 already are prime, right? We have 7, 13, and then 19. Oh, this is 25. That's not prime anymore. So 7 doesn't work. What about 5? We thought about 5 earlier. 35, that's at the end of the list, isn't going to be prime. So we could try 11. That's another prime that I know. 11, 17, 23, 29, oh, 35 right here. Doesn't work. What about 13? Now 13 plus 12 is 25. 17, no, 17 plus 18 is 35. That's not prime. We've tried at least, as proof by exhaustion, we've tried like six numbers and it's not working, so it must not be possible, right? Oh, I wish we could just say that. That would be nice.
Each of these keep adding by 6.
Pardon me?
Each of these add by 6.
Yeah, we're adding by 6, aren't we? It's like we're adding by 6. That's a good point.
Are there infinite number of primes in the form of 6p plus something?
6n plus, yeah, you could definitely argue that there are. But this isn't really looking at that whole infinite list, it's just looking at like the first few numbers of this form. By the way, I should just mention right now, I'm not actually a big fan of true-false questions on an exam, even though I'm doing a couple of them right here in the review. I just feel like usually true-false items are kind of like, mentally, like, you second guess yourself, right? Like, you have a 50-50 chance that it's right, but then I find it's just really stressful. It just doesn't work out too well. What I would be more likely to do, because this one is definitely harder than the first part. The first part I wouldn't feel too terrible about doing, but what I would be more likely to do would be to give you the answer and then just ask you to justify it. Okay? And it absolutely is the case that this is false. Okay? It is not true. You cannot find an integer such that all of those are prime. Okay? So somehow in this list of 6 numbers, there always has to be one of them that is composite. Okay? One of them that has a factorization into 2 or more composite factors. So what we've got to do is try and figure out how to prove that, justify that. Does anybody have an idea? What do we do? adding 6,
The only thing that came to mind for me first was since random six,
yeah.
X would have to be in the form 6k plus 1 or 6k plus 5.
Yeah, it's supposed to.
Well, oh, I see. So right, because these are all going to end up being congruent to either 1 or 5 mod 6. If they are all prime, then, right, every number, okay, so every number can be written in one of these forms, right? You do know this. Where q is an integer, every integer has one of these forms. That's by what result? The division algorithm, right. So, however, this is not a prime, and neither is this, and neither is this, and neither is this. So, if we assumed by way of contradiction that there was an x such that all of these were prime, let's say what we could do is we could take, say, the first case. Suppose that x is 6 cubed plus 1, then x plus 6 would be 6 cubed plus 7, and x plus 12 would be 6 cubed plus 13, and x plus 18 would be 6 cubed plus 19, x plus 24 would be 6 cubed plus 25, and x plus 30 would be 6 cubed plus 31, right? So that would be the form of the 6 numbers that we have. Is there anything obvious here why they wouldn't, why these couldn't be all prime? Certainly, these numbers are certainly all odd. They are all of the form 6 cubed plus 1, right? So they all have this form, which is one of the forms that a prime number could have. So to me, it looks like I don't really know how to go from here. But actually, the ironic thing is, Davey, is that you're on the right track. in that we want to use the division algorithm here. We want to take this number x and put it into a particular form. The only thing is, this is not the form that we want to use. We don't want to use the divisor of 6, because in the world of mod 6, as soon as x fits this form, then when you add 6 to it a bunch of times, you just keep getting more and more numbers of the same form, and that means that all of them could still be prime, because this is one of the forms that you could have a prime with. So I actually don't want to divide by 6 in my division algorithm. Can somebody think of another number that we could divide by instead of 6? 3. So if we took, what did you say? I thought I heard somebody say the right answer.
I said 4.
4?
I thought 5.
5 is the right answer. I'll come back and explain that in a second. So the thing with 3, see, the thing with 3 is, so if you tried 3, you're going to immediately, well, sorry, the only way you could have a prime number would be one of these two cases. And it's going to be the same old thing. If you add 6 to either of these, you're going to get something of the same form again. Right? But look what happens when you divide by 5. Okay? So, by way of contradiction, I'm going to start the solution now. Let's write x as 5q plus r, where r is between 0 and 4, including 4. Right? So we have those different cases. So here's the thing. So like, for example, let me just look at one case of this. Okay, suppose that x is equal to 5q. Now, if x is equal to 5q, then we already, well, first of all, it's not prime unless q is 1. And if q is 1, then x was 5, which meant